Assalamu alaikum wa rahmatullah. Welcome to our last session of our lesson, which is balancing redox reactions. At the end of this video, you'll be able to solve exercises related to concentration of ions in redox reactions. The materials needed during this session are a pen and your chemistry booklet. Let's recall back. First, in order to balance a redox reaction, balance the atoms that are reduced or oxidized. Then balance the oxygen atoms by adding water molecules H2O to the side that needs oxygen. Balance the hydrogen atoms by adding H plus ions to the side that needs hydrogen. And then balance the charge by adding electrons. In a disproportionation reaction, an atom of the same element is simultaneously, at the same time, oxidized and reduced. We'll solve exercise 2, page 21 in your booklet. First, 1 gram of KiO3 is dissolved in 100 milliliter water in a beaker A. 1.66 grams of Ki is dissolved in 100 milliliters of water in another beaker B. The two solutions are mixed and excess H2SO4 is added. It's very important here to note that the two solutions are mixed. It means the volume of the solution is now 100 milliliters and 100 milliliters equal 200 milliliters. First, calculate the initial concentration of IO3- and I- in the mixture, given that the molar mass of KiO3 is 214 gram per mole and the molar mass of Ki is 166 gram per mole. After mixing two different solutions together, the initial concentration of each substance changes as well as the total volume. Since the total volume changes, then the concentration of the solution changes. By definition, the initial concentration of a species A in solution is concentration of A initial equal to the initial number of moles over the total volume, which we said that it is 200 milliliters, where initial Na is the initial number of moles before mixing and V total is the total volume of the solution after mixing. Now we have to determine the initial number of moles of each reactant in order to find the concentration after mixing. First, the number of moles of KiO3 is equal to its mass over the molar mass, the mass which is 1 grams over the molar mass 214 gram per mole equal 4.7 times 10 exponent minus 3 moles. And the number of moles of Ki is equal also to mass over molar mass equal 1.66 grams over 166 gram per mole equal 0.01 moles. Now the initial concentration of KiO3 initial 0 is equal to its number of moles over the total volume of the solution, which is 200 milliliters or 0.2 liters equal 4.7 times 10 exponent minus 3 over 0.2 equals 0.0235 mole per liter. And the initial concentration of Ki 0 at time 0 is equal to its number of moles over the total volume of the solution equals 0.01 moles over 0.2 liters equals 0.05 mole per liter. But we are asked to find the concentration of IO3- and I-. IO3- comes from the dissociation of KiO3, which gives K plus and IO3-. Here, according to the stoichiometric ratio of this dissociation reaction, concentration of KiO3 over 1 is equal to concentration of IO3- over 1 equal to 0.0235 mole per liter. And in order to determine the concentration of I-, we write the equation of dissociation of Ki, which gives K plus and I-. Also, the concentration of Ki over its coefficient according to the stoichiometric ratio, which is 1, is equal to concentration of I- initial over its coefficient, which is 1, equal to 0.05 mole per liter. Now in part B, we have to identify the limiting reactant. The balanced equation of the reaction is IO3- plus 5I- plus 6H plus give 3I2 plus 3H2O. Here, don't forget that H plus from H2SO4 is in excess. We said that KiO3 dissociates in water giving K plus and IO3-. Then according to the stoichiometric ratio, number of moles of IO3- over 1 is equal to number of moles of KiO3 over 1. Now the ratio in this reaction of IO3- is equal to the number of moles of IO3-, which is equal to number of moles of KiO3 equal 4.7 times 10 exponent minus 3 over 1 equal 4.7 times 10 exponent minus 3. Also, Ki dissociates, giving P plus and I minus. Then, according to the stoichiometric ratio here, the number of moles of I minus is equal to the number of moles of Ki over 1. And the ratio of I minus here in this reaction is equal to number of moles of I minus over its coefficient, which is 5, equals 0.01 over 5, equals 0.002, or equal to 2 times 10 exponent minus 3. By comparing the stoichiometric ratios, we find that the ratio of IO3 minus, which is 4.7 times 10 exponent minus 3, is greater than the ratio of I minus, which is 2 times 10 exponent minus 3, then I minus with the smallest ratio is the limiting reactant. Deduce the concentration of I2 at infinity or at the end of the reaction. The balanced reaction was IO3 minus plus 5I minus plus 6H plus give 3I2 plus 3H2O. According to stoichiometric ratio, the number of moles of I minus, which is the limiting reactant, over its coefficient, which is 5, is equal to number of moles of I2 over its coefficient, which is 3. Here, because they are found in the same solution, they have the same volume, then we can divide by the volume of the solution. Then we get number of moles over volume, which is concentration of I minus initial over 5 is equal to concentration of I2 at infinity at the end of the reaction over 3. Then concentration of I2 at infinity is equal to 3 concentration I minus initial over 5 equal 3 times 0.05 over 5 equals 0.03 mole per liter. Find the concentration of the excess anion remaining at the end of the reaction. We said that IO3 minus is the excess reactant. Then, according to stoichiometric ratio, the number of moles of this reactant, IO3 minus, reacted over its coefficient, which is 1, is equal to number of moles of the limiting reactant, I minus, over 5. Then, the number of moles of IO3 minus reacted is equal to 0.01, which is the number of moles of I minus, over 5, equal 2 times 10 exponent minus 3 moles. Now we can determine the concentration of IO3 minus reacted by dividing the reacted number of moles of IO3 minus over the total volume of the solution, equal 2 times 10 exponent minus 3 over 0.2 equals 0.01 mole per liter. Now, the concentration of IO3 minus remaining is equal to the initial concentration of IO3 minus minus the concentration of IO3 minus reacted equals 0.0235 minus 0.01 equals 0.0135 mole per liter. In the last part, you are asked to prove the following relation. Concentration of IO3 minus at instant t is equal to 2.353 times 10 exponent minus 2 minus 0.33 concentration of I2 at any instant t. Here, we start by saying that the number of moles of IO3 minus at any instant t is equal to number of moles of IO3 minus initial minus number of moles of IO3 minus reacted. This is the reactant IO3 minus, so we can write this relation. Now, according to stoichiometric ratio of this reaction, we say that the number of moles of IO3 minus reacted over its coefficient 1 is equal to number of moles of I2 formed over 3. Now, we can say that the number of moles of IO3 minus at any instant t is equal to the number of moles of IO3 minus initial minus, instead of number of moles of IO3 minus reacted, we write number of moles of I2 over 3. We divide by volume of the solution, so we get number of moles over volume is concentration of IO3 minus at instant t is equal to concentration of IO3 minus initial minus concentration of I2 over 3. The concentration of IO3 minus initial was 0.0235, or it is 2.353 times 10 exponent minus 2 minus 1 over 3 equals 0.33 concentration of I2. Now we'll solve exercise 1, page 24, dilution of a commercial solution of hydrochloric acid. Consider a beaker containing a commercial solution S0 of hydrochloric acid HCl. On the label of this beaker, we read the following indications. Density is equal to 1.12 gram per milliliter, percentage by mass equal 32.13%, and molar mass of HCl is equal to 36.5 gram per mole. Show that the molar concentration of the solution S0 is C0 equal 9.86 mole per liter. First, we know that the percentage by mass of any solute is equal to the mass of the solute over the mass of the solution times 100. But we have C0 is equal to number of moles of solute over volume of the solution. Then the number of moles of the solute is equal to C0 times volume of the solution. And the number of moles is also equal to mass of solute over molar mass. Then the mass of the solute is equal to N times molar mass, and N is equal to C0 times V. Then we write the C0 times molar mass times volume of the solution. And the density is equal to mass of solution over volume of solution. This is the density of any solution. Then the mass of the solution is equal to density times volume of solution. Therefore, the percentage by mass is equal to mass of solute, which is C0 times molar mass times volume of solution, over the mass of the solution, which is density times volume of solution, times 100 is equal to C0 times molar mass, okay, over density times 100. Hence, in order to determine C0 here, it is percentage times density over molar mass times 100 equal 32.13% times 1.12. The density here is in gram per milliliter. We have to change it into gram per liter. To convert it into gram per liter, then we multiply it by 1000 over 100 times the molar mass, which is 36.5, equal 9.86 mole per liter. In part 2, by dilution of solution as 0, we prepare a solution as, that is then titrated by a sodium hydroxide solution, NaOH. The concentration of S of the new solution is found to be equal to CS, concentration of S equals 0.07 mole per liter. We consider the following two groups of glass materials. First, group A, which contains a volumetric flask of volume 1000 milliliters, a graduated pipette of 10 milliliters, and it is graduated to 1/10, and a beaker of volume 50 milliliters. A group B, which contains a volumetric flask of 100 milliliters, volumetric pipette of 2 milliliters, and a beaker of 50 milliliters. Explain for each group if it is convenient to make this dilution. Now, according to dilution principle, the number of moles of solute HCl is conserved. That means that the number of moles initial before dilution is equal to number of moles final after dilution. The dilution factor X is equal to V final minus V initial, or it is equal to C0 over C final. C0, which was 9.86, and C final, which is 0.07 mole per liter, equal 140.8. Where V final is the volume of the volumetric flask and V initial is the volume of the pipette. For group A, if V final is equal to 100 milliliters, then X, which is equal to V final minus V initial, and V initial is equal to V final over X. V final, which is the volume of the flask, which is 1000 milliliters, over X, which is the dilution factor, which is 140.8, equals 7.1 milliliters. But can we take this 7.1 milliliters using a 10 milliliter graduated pipette, which is marked 1/10? Of course we can. So 7.1 milliliters can be withdrawn by a graduated pipette, 10 milliliters marked 1/10. So we can use group A. For group B, we have V final, which is equal to 100 milliliters. Now we can determine V initial, which is equal to V final over X, equal 100 milliliters over X, which is 140.8, equals 0.7 milliliters. Can we take 0.7 milliliters by a 2 milliliter volumetric pipette? Of course we cannot. Then 7.7 milliliters cannot be withdrawn with 2 milliliters volumetric pipette because it can only remove 2 milliliters. Therefore, the most convenient is group A. Now, as a summary, let's remember how to determine the initial concentration of a commercial solution. First, the percentage by mass is equal to the mass of solute over mass of solution times 100. We have C0, which is equal to number of moles of solute over volume of solution. Then the number of moles of solute is equal to C0 times V solution. And number of moles is equal to mass solute over the molar mass. Then the mass of the solute is equal to number of moles times molar mass, equal, instead of number of moles, we write C0 times V solution times the molar mass. and the density of the solution is equal to the mass of the solution over volume of the solution, then the mass of the solution is equal to density times volume of solution. Therefore, the percentage by mass is equal to mass solute over mass solution times 100, mass solute, which is C0 times molar mass times V solution, over, instead of mass solution, density times V solution times 100 equals C0 times molar mass over density times 100. Hence, concentration, initial concentration of the commercial solution is equal to density times percentage by mass over 100 times molar mass. This session was prepared and recorded by Mr. Mustafa Tlais and supervised by teacher Hiba Badawi.